But suppose you did
Well,
not.
I guess I was muted, so we're going to go ahead and get started on this lesson.
Here, or perhaps even here. Our question will be, how can we know the maximum distance between the first and third locations, or even the minimum distance between the first and third locations, if we know two of the distances?
Not within A triangles, but just within triangles related. Let's go ahead and hit that with that. Let's go ahead and hit that with that. Maneuver this just a little bit up so we're good. Now we should be ready to roll.
Your main lesson goal is to analyze triangles, sides, and angles. And how will we do this? We'll investigate the relationships between angle measures within a triangle, and we will determine the necessary criteria for segment lengths to form a triangle. Look at some keywords we need to know and make sure you include them in your e-notes or look them up in your glossary. We have acute triangle, equilateral triangle, isosceles triangle.
I'm going to pause these real quick just to show you this is where you get them from right here. I already know the meanings of all these ones, so I'm going to go ahead and go. I'm gonna go ahead and let this play out, but this is where you get these ones. So and all you do is in this one, like right here, this is an acute triangle, a triangle whose angles each measure less than 90 degrees. So that's an acute triangle, which means acute is small. So that just means like small angles. So that's how easy it is to go. But make sure you guys do that. Pause this video right here at this point till you have this as you need. But if not, I'm gonna go ahead and let this play while I fill out these ones right here on my own.
Obtuse triangle, right triangle, and scalene triangle. Triangles are classified by both sides and angles. If I have an acute equilateral triangle, as we do here with triangle DFE, it is acute because all three angles are acute. And it is equilateral because all three sides are congruent. Look at the second triangle. Second triangle is a right isosceles triangle. That's triangle OPR. Why is it right? Well, because it contains one right angle. Why is it isosceles? Well, it contains two sides of equal length. In our third triangle, it's an obtuse scalene triangle. That's triangle JKL. And why is it obtuse? Well, because it contains one obtuse angle. And why is it scalene? Well, it's scalene because it contains three sides of three different lengths. Determine which type of triangle is described under each set of conditions.
Okay, so in triangle ABC, measure of BAC is equal to 50 degrees. Okay, so if the measure of ACB is 30, then that means that's 30, 50. So then that means that this will be an obtuse, because an obtuse is going to be your a triangle that has more than one. So if I add these two together, that's 80. So then that's 100 for the third angle. So that means that's more than 90 degrees. That makes it an obtuse. So this one here is a 40 and 50. So that's 90. So then that means that this one is going to be a right triangle, because the right triangle is at 90 degrees. If a triangle ABC is isosceles, and isosceles means a triangle having at least two congruent sides, and AB is 6 and BC is 4, then AC has to equal 4 or 6. It doesn't matter. It just two of them have to match. Okay.
Now let's look at triangles in which distinct angle measures are not always given. You've learned how to classify triangles as acute, obtuse, or right, as well as also equilateral, scalene, or isosceles. But how are angle and side lengths in a triangle actually related? Angle E in this triangle is obtuse, clearly, 120 degrees. Any triangle with angle E as a vertex is going to be an obtuse triangle. Our goal in this segment, we're going to learn how to examine the relationships between angles in a triangle and different classifications of the triangles. In this diagram, angle BAC is an obtuse angle. The definition of an obtuse triangle is any triangle with an obtuse angle at a vertex. The question is, can an obtuse triangle have two obtuse angles?
No.
No, let's try it. Let's go to point B, and let's draw a line segment from B to D. This angle right here is obtuse. Now notice, we have 1, 2, 3 sides. And with two obtuse angles, it is impossible to draw a triangle because we have a fourth side that would be needed.
That's not even a triangle no more. That's now like an octagon. Well, not an octagon because that has 8 sides, but this one has more than 3 sides, so that's now considered something else.
Determine which statements could be true of triangle LMN.
If triangle LMN has an obtuse, which means more than 90, angle at vertex M, which statements could be true? Triangle LMN is an obtuse triangle. Has to be. It tells you right there it has an obtuse angle. The angle at vertex L is acute. That is true because that's a smaller angle, because an acute triangle is a triangle that has 3 measures. Nope, it's not a acute. Well, I'm gonna try that one because acute means that it's smaller. So it's not saying that it's an acute triangle, but it is saying that it's an acute angle. So I'm gonna leave that one. The angle at vertex L is a right. That there's no guarantee of that. The angle of vertex N is a right. There's no guarantee of that. And it really can't be because this one is an obtuse angle, so that means it's greater than 90, so that means it's the biggest angle. So there's no way you could have 100 and then a 90 because that's 190 degrees. There's no way a triangle could have that much degrees. Angle of vertex N is acute, so I'm going to say that that one also is. And no, I'm just going to go with those 3.
Now let's determine how to use angle measure comparisons to determine why 2 angles in an obtuse triangle must be acute. Take a look at angle PQR. Notice that this angle is an obtuse angle. So if I go ahead and then create any triangle with an obtuse angle, what do we notice? Well, first of all, that the measure of angle P plus the measure of angle Q plus the measure of angle R must sum up to be 180 because the sum of the 3 and 3 angles of the triangle is 180.
Mm-hmm.
What else do we notice? Well, as we noted, the measure of angle Q, this obtuse angle, that's greater than 90 degrees. Now think about this just for a second. If we know that the sum of the measures of the triangle must be 180, well, that means the sum of the remaining 2 angles,
which is this one and this one,
angle R, their sum must therefore be less than 90 degrees. And so we can now generalize and say for any obtuse triangle, the sum of the 2 remaining angles that are not obtuse, they must be less than 90 degrees.
And not equal to 90 degrees. It won't be, if it's a 90-degree triangle, it'll be a right triangle. So if an obtuse, that means it's a 91 degrees. So then that means the other 3 have to be 89 total.
Determine the angle relationships within triangle XYZ.
Okay, so the vertex is Y, which means the right triangle at vertex Y. So X must be acute, Z must be acute, and the sum of the triangles must be equal to, because it's a right triangle. So that means it's a right triangle is equal to 90. That means that the other 2 angles have to equal to 90. So those ones could be that's what it would have to be.
We have examined how angles within a triangle are related. Now let's examine how side lengths are related. You've been doing a really good job answering the question, how are angles and side lengths within a triangle related? What have we done? Well, we've been analyzing different types of triangles. And we've noticed that some triangles don't exist, like obtuse triangles with 2 obtuse angles.
Mm-hmm.
What are we going to do next? Well, we'll turn our attention to determining the side length parameters to see what types of triangles do and don't exist. Within each set, drag the segments until you either make a triangle or determine that a triangle with those side lengths does not exist.
Okay, so try to form a triangle by dragging point A and D. Is it possible to form a triangle with side lengths 1, 5, 3, and 3 units? So there's no way, because these won't even connect. If you could get those to connect right there like that, you would, but there's no way that you can. So there's no way you can do that. Is it possible to form a triangle with lengths 3, 4, and 5 units? Same thing. Let's just try to see if we can do this. Well, we might be able to. No, is there any way we can meet them up here? Oh, okay, so we met them up there. So yes, there is a possibility that we could do that one. Okay, so now with length 3, so let's see if we could do the same thing here as we did on that one. Oh, they're just short. Could we make it? Could we make it? Oh, they look like they do. I'm gonna say no because they didn't give me like the last one. Okay, so now these ones have to be way up here. So let's see if we can combine them. These ones look like they're gonna go. Yeah, those ones look like they're gonna go. So that one's yes. Okay, so is it possible with sides 2, 4, and 5? So we're here and we're here. Can we? Yeah, that one did it too. So that's a yes.
Why is it possible that some side lengths can be used to create triangles, but not others? How do you think the side lengths of the triangles are related?
I think it's because of the Pythagorean theorem. So this is it. A squared plus b squared equals c squared. So I know that this is 9, this is 16, this is 25. So 9 plus 16 equals 25. This is 25, 25, and 3. So this is going to be 9 and 25. I don't know why this one didn't. I don't know. We're going to have to look into that one because I believe that it should.
The triangle inequality theorem. This states the sum of the lengths of any two sides of a triangle is going to be greater than the length of the third side. In other words, any two sides of a triangle must add to be larger than the third side.
Mm-hmm.
Now, for example, here is side C. It is going to be smaller than the sum of the lengths of A and B.
Mm-hmm.
And here is side B. Right here. It is going to be smaller than the sum of the lengths of sides A and C.
Mm-hmm.
And right here, side A is going to be smaller than the sum of the sides B and C.
Mm-hmm.
Well, a different way of thinking about this theorem is that each possible pair of the two sides must subtract to be smaller than the third side. In other words, it's not far-fetched to take this inequality and think about it a little different, that C minus A must be less than B, or C minus B must be less than A. And we can do this with any of the three inequalities. We can say that B minus A must be less than C, or B minus C must be less than A. Going to the third inequality, and again, rewriting it, we can say A minus B must be less than C, or what? Or A minus C must be less than B.
Mm-hmm.
Notice the inequality at the bottom of the screen. What it says is that if you take the difference of two sides, this will be less than the third side, which will be less than the sum of those two sides. For example, suppose we had A to be equal to 10 and B is 4. Now the third side is C, isn't it?
Mm-hmm.
So this inequality says that A minus B, or 10 minus 4, must be less than the third side C, which must be less than the
6.
sum of the two sides. Well, that would be less
14.
than 10 plus 4.
Side C is between
In other
6
words,
and
we would say that 6
14
would be
units.
less than C would be less than 14. In other words, side C would be between 6 and 14 units. This is a strict inequality because there is no or equal to underneath the symbols.
Okay. Something you probably got to pay attention to, and you kind of got a grasp in here. I bet you we're going to do something that makes us try it right here.
Determine the possible distance between the two cities.
Well, you can't even really see them, but hey, that's all right. What was that little gateway thing that just popped up on screen? Never seen that before. Okay, so assuming the three cities make a triangle, so Lincoln in Boulder, Colorado. Okay, so Lincoln and Boulder are 500 miles away. the distance between Boulder and the third city is 200 miles, assuming that these three cities make a, so here, so this is the main line here, so I'll go ahead and annotate that one real quick. So we're saying, because Boulder, I know Boulder, Colorado is about right here, and I'm just gonna say that it's somewhere right there like that. Okay, so there's my first line. Okay, so that's the longest one because the other one is 200 miles. So I'm gonna assume that maybe we're talking about right here because I'm gonna say it's a line about half, roughly around half. Okay, so now let's, assuming the three cities make a triangle on the map, which values represented the possible distance D in miles between Lincoln and the third city? Well, we know that A minus B, which is 5 and 2, so the difference is there. And when you add them together, which is A plus B, okay, so let's try this again. The three cities make up a triangle. Lincoln, Boulder would be A and B. So let's see, would that be A and B are 1,000? And 5 and 2 is 7. Sorry, guys. 8, I don't know what I'm thinking. 5 and 2, 5 minus 2 is 300. 500 plus 200 is 700.
Now, let's prove the triangle inequality theorem. Given a triangle, what we want to prove is that the sum of the lengths of any two legs is greater than the third leg of the triangle. Given triangle ABC, I want to prove that if I sum up lengths AB and AC, that'll be longer than the length of the third side, BC. Now, how do I do this? Well, the very first thing I'm going to do is I'm going to draw a perpendicular line segment from vertex A to segment BC.
Ours already has it.
There's my perpendicular line segment, and I'm going to label that point its intersection E.
Perpendicular also gives the right triangle.
Now, what we know quite specifically is that if I go through point B to line segment AE, the shortest possible distance will be that line that connects the point to the line segment with the perpendicular line segment. Well, that means BE is the shortest line segment that goes from B to AE. Now let's think about this. Do you see another line on this diagram that goes through B and connects AE? Now, I do. That's AB. And because BE is the shortest distance that will connect B to AE, AB has to be greater than it. That's what we're saying here, that BA is greater than BE. Don't lose that thought, because all I'm going to do is say, let's pick another point, and the other point we're going to pick, ladies and gentlemen, is point C. And we're going to say the shortest distance from point C to line segment AE is the perpendicular through point C to AE. Well, that's line segment CE. So any other line that goes to point C and hits up to AE, like this line right here, AC, has to be longer than CE. That sentence is what we see right here, that AC is greater than CE. Now, all I really want to do is simply add the inequalities. All right, so if I add the inequalities, then I'm going to go ahead and say that BA plus AC is going to be greater than BE plus CE. Well, let's look at BE plus CE for a second. Here is BE, here is CE. And we know the segment addition postulate simply says that BE plus CE is equal to BC. So I'm just going to simply make that substitution. And when I make that substitution, I end up with BA plus AC is now greater than BC. And that's what we were trying to show, that the sum of two side lengths is greater than the third side length. And if I went ahead and just simply drew a perpendicular from B to AC, I can now show that two different line segments would be greater than the third. And if I was to drop a perpendicular from C to AB, I could still show two different line segments of this particular triangle would be greater than the third. So it would hold for any pair of line segments when compared to the third for any triangle. Complete the proof of the triangle inequality theorem.
Okay. So in a triangle ABC, we can draw a perpendicular line segment. So I'm gonna draw the perpendicular line segment from here, and I'm gonna go as straight down as I possibly can. Okay. And from the vertex C to segment AB. Okay, so that's I was wrong. So we're gonna go from here, perpendicular, which I'm gonna assume is about, I can kind of see the pixels on it. So I'm gonna say that that's about right there. To me, that looks about right. Okay, so the intersection of AB and the perpendicular is called E. We know that BE, so let me go ahead and text that right there and put an E right there. Okay, so that's E. This is point E right there. And we know that B is the shortest distance from B to okay, so we're perpendicular line from the vertex to segment AB. Got that. The intersection of AB and the perpendicular line is called E. We know that BE is the shortest distance from B to CE. No. CE, and AE is the shortest distance from A to CE because of the shortest distance theorem. Therefore, BC is greater than BE, and AC is greater than AE. Next, add the inequalities. BC plus AC is greater than BE and AE, then B and AE are equal to BA because of the
The sum of the lengths of the two sides of a triangle will be greater than the length of the third side.
Very tricky.
An isosceles triangle is a triangle with at least two congruent sides. We are going to make an isosceles triangle with exactly two congruent sides. Now look at segment PQ. Off on the side, you see segment RF.
So it's already done for us here.
Segment PQ. What I'm going to do is I'm going to drag my compass over and notice, oh, look what happened. The width of the compass is exactly the length of RS. So I'll go over to point P and I'll rotate an arc. And I'll go over to point Q and I'll rotate a second arc. And what do you notice? Those two arcs intersect. So if I go ahead and allow myself to put one side of the triangle to start at the intersection and the other end of that side to go to Q, and then create a second line, and my second line would start at that point of intersection and end up at point P. I create an isosceles triangle with exactly two congruent sides. Why is this an isosceles triangle? Well, the length of the side is exactly the radii of two congruent circles.
Okay.
Use the instructions to construct an equilateral triangle.
Okay, so let's review real quick, because an equilateral triangle, and this is why you got your notes right here, guys. This is why we do this. But equilateral is a triangle having 3 congruent sides. Okay, so on the last example, they wanted you to have 2 congruent sides. So this one's gonna be 3 congruent. So all we're gonna do is we're gonna have this, and we're just gonna get to this point right here and have it on here. We're gonna move it out to this angle here, and then I'm gonna rotate it. I wonder, ooh. Okay, so I guess I gotta start drawing already. Right there, like that. Now what I'm gonna do is I'm gonna reverse this. I'm gonna put this on this side, and then I wish I can, I don't know how I gotta do it like that, but look, you can see that it's there. Now what I'm gonna do is I'm gonna move that out the way. I'm gonna use this right here, just like that. And to this one, I'm gonna go right here and right here. And now all 3 of those are
equilateral
perfect.
Because the sides are radii of congruent circles.
Go back down to where I was in my notes.
Isosceles triangles can be acute, right, or obtuse. Take a look at triangle STQ. Now this is an acute triangle because all the angles are less than 90 degrees. And if you note the congruent marks,
2 of them.
PQ is congruent to QS. This means it's an isosceles triangle. So it's an isosceles acute triangle. We also have a triangle PQR. And if you note these notation for perpendicular lines meeting, this means that we have a right triangle because angle Q is 90 degrees. And again, if you note the congruent marks, sides RQ and QP, well, they're congruent. So we have a right isosceles triangle. For the last triangle in this figure, we see triangle SQP. And we note a obtuse angle, angle Q. And again, note the congruent marks. So we have 2 congruent sides. So we have a angle that's greater than 90, angle Q. And so we have a obtuse isosceles triangle. Now, turn our attention to equilateral triangles, where we have 1, 2, 3 sides that are congruent. These triangles are also going to be isosceles triangles. Note a very important facet of this triangle, that all the angles must be less than 90 degrees. In other words, we have an acute triangle. Why is that so? Imagine increasing a single angle. So I'm going to increase this angle. Now remember, the side lengths are the same. So this side length is still the same as these 2. That means that 2 sides would never meet up if that angle was increased. Note, if you will, also, that if you turned around and again noted the 3 congruent sides, but decreased an angle in length, again, all the side lengths are the same, so one side would most assuredly overhang the other. So this tells us that we have an acute triangle, and more importantly, we have an acute isosceles triangle. Why is it isosceles? Well, the formal definition of an isosceles
less than 90
triangle is that
degrees.
you have at least 2 congruent sides. And equilateral triangles are isosceles because they do have at least 2 congruent sides because they have 3 congruent sides.
All right. There's your instruction video. I'm gonna go ahead and get this one downloaded and ready to go so I can put this up in the YouTube channel that we have for this classroom. And I'll have this up in a minute. I'll be back in a bit with the assignment portion. We'll see you guys in a bit.